Hello everybody, welcome to the 10.5 video, which is starting solving exponential and logarithmic equations. And during this 10.5 video and 10.6 video, you're going to start to notice how important understanding the idea of using inverses is, as well as being able to expand and condense logarithms quickly to help you solve these equations. But before we get to these specific types of equations, I would like to first focus on some other equations that you already know. I would like you to pause the video in just a minute, and I'd like you to solve all 8 of these equations. I would like you to think about, while you're solving, what the relationship is between the bunches of equations that I'm putting together right now. I would assume, by the way, that if you're going to solve these equations with tangent, let's go ahead and make sure, if you're going to do that, put your calculator in radians. So please pause the video now and solve these to the best of your ability, and I will come back with my answers. Please pause now. All right, so here are all my final answers for these equations, some of them more quick than others. And the relationship that I hope you noticed while you were solving is that these first 2 equations were solved by using inverses. If you had a plus, you used subtraction to get rid of it, an inverse operation. If you had subtraction, you used addition, which is an inverse operation. Same thing goes with the next 2 equations. When you had multiplication, you used the inverse of division, division to the inverse of multiplication. Same when it came to radicals. If you had x cubed, the inverse is the cube root. If you have a cube root, the inverse is cubing. If you think back to first semester with tangent and arctangent or inverse tangent, if you had tangent originally, you would take the inverse tangent or arctangent of both sides, and you plug that into the calculator like this, and this was the answer in radians. And if you were given the inverse originally, you'd apply the tangent on both sides, because again, they're inverses, and you get a final answer of tangent of 4, or 1.158. So feel free to pause and copy any of that down that you need. But the reason that I wanted to do this was to transition into the idea of inverses. That if we look at these 2 equations down here, this equation is originally exponential. So it would make sense to me that if we would like to solve it, we'd like to use some kind of log or ln, because those are inverse operations. And if you're given a logarithm here, it would make sense that you want to eventually use exponents or change it into an exponent, because those are inverses as well. So if I write this equation over here, e to the x equals 4, so I have a little bit more room, we have an exponential equation. So if we don't know what else to do, we can introduce a logarithm on both sides. Because this is base 3, I would introduce log base 3 on both sides of my equation. So I would have log base 3 of 3 to the x equals log base 3 of 4. Now, what's nice about this side is when you have log base 3 of 3, these end up being inverses because exponents and logs are inverses, so you'd really just be left with x, because the x technically comes in front, and you're multiplying that by log base 3 of 3. And if you think about what this means, log base 3 of 3 really means 3 to the what equals 3, which is 1. So this, in a way, cancels out. So you get the answer of x equals log base 3 of 4. Which is interesting, because that is the equation that I start with on the next example. And yes, this is technically a decimal. You could plug this into your calculator and get a decimal for that. But in order to plug this into your calculator, I'd like to remind you about the idea of the change of base formula. In the calculator, we do not have a log base 3. So if you'd like to make this in terms of base 10, you would take log of 4 divided by log of 3, the argument divided by the base. And if you did that, you would get 1.262. So change of base is very nice when you do not have a base of 10 or e. If I recopy the second equation down here, log base 3 of x equals 4, I like this one even better because we're given a logarithm. What if we change it to an exponent, so that we're using exponent logic so that we could solve this? This reminds me of what we did earlier in past videos. The base of this logarithm is e. The exponent of the logarithm must be 4 because logs are exponents, and that must equal x. So x must be 3 to the 4th, which is 81. I like when things are logarithms. Changing them to exponents is usually much faster. But these ideas, again, are inverses, that when you have the 1, you apply the inverse to help you solve it. Speaking of solving, below here, let's talk about options for solving logs and exponentials. So let's start with logs. If you would like multiple ways to write down to consider solving a logarithm, what you could do is first use exponentials to solve, or think of it as change to an exponential equation. That's one option. Something you'll realize as we keep going through the next couple of videos, other options, is you could make the equation into a single logarithm, which when you're going to be using the condensing idea of logs. And something else you'll see is if you can get the equation to be log base b of something equals log base b of something else, because it's the same log, same base on both sides, the arguments here would end up being equal. So if you can get log equals log, that could be an easy way to solve as well. On the other side, if you're given an exponential equation, there's multiple ways, again, you can solve these, and they'll make more sense as we go. You could first, if you have an exponential equation, write both sides with the same base. You'll see that very soon in the upcoming slides. So that's an option. What else you could do is take the log base b of both sides and then use the change of base formula. Sorry about my handwriting. Easier said than done on this tablet. The last option is to take a log, which you're assuming is base 10, or ln, which you're assuming is base e of both sides. And some of you might end up liking that the best because you don't have to deal with change of base formula that way. But there's a lot of different options that we can work with. And again, having them written down now is going to help you later, especially when we get into more types of equations, which are about to start momentarily. Okay, so if we start some equations, I'm going to try to show you multiple ways, but I'm mainly going to focus on the fastest way to solve something. So for this first equation, it is exponential. And when we thought back to this, what we could do is write both sides with the same base. Sometimes that's the fastest way. We could take log base whatever we have of both sides, or we could take a log or ln of both sides. In this case, I would say, because I already can see that 27 could be written as a base of 3, you could think of this as 3 to the x equals 3 to the third. And now because both bases are the same, that means that both exponents must be equal. So without much work, I know that x must be 3. Now, just for this fact of showing you though, what you could do instead is, because the inverse of an exponent is a log, you could take the log base 3 of both sides. So you'd have log base 3 of 3 to the x equals log base 3 of 27. You could bring the exponent down and have x times log base 3 of 3 equals log base 3 of 27. Just like earlier, log base 3 of 3, these are inverses, or really the exponent is 1. So you'd be left with x equals log base 3 of 27, but that is actually an answer because log base 3 of 27 is 3 to the what equals 27, which is 3. Now, you might be wondering, Mrs. Logus, why did you show us both of those if the first way is clearly faster? On a test, I would completely recommend that you do the first way, but I'd like to show you that you could use logs technically because they are inverses. The second equation, I'm actually going to have you change because I feel like it's too similar to the first one. The answer for this one would be to the second power. That's how you'd get this. But I'd like you to change this problem instead to be 16 to the 2x plus 1 equals 8. The reason I like this problem better is because when you look at 16 and 8, I want to remind you again that one of the best ways to solve an exponential, if possible, is to write both sides with the same base, if it applies. And in this case, I noticed that 16 and 8, I can't write, so 8 squared is already to 64, so I can't keep both the bases the same. But I do notice that both of these could be written with the base of 2. This side could be written as 2 cubed, and this side could be written, or the 16 itself, could be written as 2 to the 4th. But the 2x plus 1 is still there, so it would remain in the exponent position, and these exponents would multiply. Now that the bases are the same, the exponents must be equal. So we'd have a little mini equation. 4 times 2x plus 1 equals 3. So that would be 8x plus 4 equals 3. 8x equals negative 1. So my x value would have to be negative 1/8. This example, now this one, I can't change 4 to be e to a power. So this is when using logs is going to be the best way. And because I have a base of e, the inverse would be ln. So what we could do is take the ln of both sides of my equation. So I'd have ln e to the x equals ln of 4. Now that I've introduced a log, you can bring the exponent down and have x times ln of e equals ln of 4. ln and e are inverses, so this crosses out, or you could think of it as e to the what equals e, which is 1. So you have an answer of x equaling ln of 4. And yes, this has a decimal answer, but I'm going to leave it exact. The next example, ln x minus ln 5 equals 0. To relate this to things we already know, if we have 2 logs and we want it to just be one single log, which usually makes it easier, we can condense this. So 2 ln subtracted is the same thing as 1 log with the first argument dividing the second. So if I make it into one single log, I would have to remember that the base or the secret base is really e. And what we can do is change this in our minds to an exponent because it is a log currently. The base of this log is e, the exponent of this log is 0, and I know that has to equal x over 5. E to the 0th is 1 equals x over 5. So if I multiply both sides by 5, my x is 5. Not too bad. An even better way to solve this equation, ln of x equals ln of 5. Move this over at the beginning. Because this is the same log with the same base, I know the arguments must be equal, so x must be 5. 2 excellent ways to solve the same equation. This equation is originally a log, so my mind makes me think that I want to change it to an exponent. The base of this log is 5. The exponent of this log is negative 3 because logs equal exponents, and that has to equal the argument of x. So x equals 1 over 5 to the 3rd. Negative exponents flip, so 1 over 125 is your best answer. This next example, you're given exponential, which makes me think that we're most likely going to be using logs to solve it, or ln's to solve it, because we want to use inverses. But before I can do anything with inverses, I want to make sure that my exponential function is isolated. So I'm going to divide by 2 first and be left with 5 to the x equals 16. And then whenever I notice that I have the bases not being the same, the first thing I would check for to see if you can write 16 as 5 to the something, I can't. So this is when logs are very useful. Now, I would avoid using log base 5 of both sides, because when you have to do log base 5, you eventually have to use the change of base formula, which is not the fastest way. So what I would do is just take a basic log or an ln, so either log base 10 or ln of both sides. When you do that, this exponent comes down. You have x times ln of 5 equals ln of 16. Now, these don't cancel this time because they're not inverses, but what I can do is divide both sides by ln of 5. So my answer in exact form would be ln of 16 over ln of 5, which, if typed into the calculator, would be 1.723. Either of these answers are acceptable. And some of you might be wondering, why did you use ln when we had no base e? The beautiful thing about ln and just plain log is you can use them on both sides no matter what the base is. This start example we'll be using as a warm-up the next day. If you'd like to try it on your own, the answer should be 4.535. Instead, we're going to end on this one, where if we have 2 logs with the same base on both sides, turns out that the arguments would have to be equal. Same base, same exponent. So 4 plus x would have to equal 2x minus 1. And if you solve that, x would be 5.